Hello everyone and welcome back to tutorial 11 of MIE100, the dynamics course in the University of Toronto. Today we're going to talk about dynamics of rigid bodies, specifically plane kinetics of rigid bodies. It's going to be a summary of everything that we've done in the past few weeks. As always, if you have any questions, make sure you leave your question in the comments below. Okay, so starting with problem 1, we've got a uniform slender bar of mass m pivoting freely about a horizontal axis through O. If the bar is released from rest in the horizontal position shown, where the spring is unstretched, it is observed to rotate a maximum of 30 degrees clockwise. The spring constant K is 200 Newton per meter, and the distance B is 200 millimeter. Determine A, the mass of the bar, and the magnitude of the angular velocity of the bar. And the angular displacement is 15 degrees clockwise from the release position. Okay, so first of all, we need to write our known variables. So initially the velocity is 0, and the extension of the spring also is 0 because it's unstretched. The maximum rotation is going to be 30 degrees clockwise. The spring constant is 200 newtons per meter, and the distance B is 200 millimeters, or 0.2 meters. Okay, so first of all, position 1 looks kind of like this simplified. This is A, this is B, this is C, this is spring K, and this is O. While in position 2, this is kind of what it looks like. This is A, B, O, and this is a spring K. Assuming that the center of gravity is around here, it's also going to be around here, and we want to find the distance from A to C. So basically, this is an exaggerated version of it, but if we want to find A to C, then we also need to find C to D, D to O, and O to A. So the position of A with respect to C is going to be equal to the position of A with respect to O plus the position of O with respect to D plus the position of D with respect to C. So if we plug in our known values, our OA is going to be equal to 3/4 B minus cosine theta in the I direction and plus sine theta in the J direction. Plus B over 4J for for the position of O with respect to D, plus 3/4 BI for the position of C with respect to D. Now if we add that up, it simplifies to 3/4 B minus 3/4 B cosine theta in the I direction, plus B over 4 plus 3/4 sine theta in the J direction. And if we want to find the magnitude of this position vector, we can get after it's simplified, we can finally get B over 4 6 sine theta minus 18 cosine theta plus 19 all under the square root, and that is valid for any value for theta. Now let's get back to the question. We want to find the mass. So first of all, to find the stretched and unstretched length of the spring over here, any change that happens from A to C will also cause a change in the stretched length of the spring. Therefore, we can assume that the magnitude of AC, the unstretched in position 1, is going to be equal to the unstretched length of the spring. So to calculate that, we can plug it into this equation over here, so that, or we don't even need to plug it into this equation. This equation is just going to simplify it back to what we know here, which is B over 4. So, hello, it's just going to be B 0.2 over 4, which is equal to 0.05 meters. Now, if we want to find the length L2 of the spring, it's going to be equal to the change of AC. So AC in position 2 is going to be equal to the length of the spring at position 2. So to calculate that, we can plug it into this equation over here. And plug in our theta 30, because that's the maximum. To give us maximum value of AC, which is 0.127 meters, which is also equal to L2. Okay, now if we want to find the change in length, so we've got the final length and the unstretched length. Final length is just going to be L2 minus L naught, which will give us 0.07 meters. Okay, now that we've got that covered, we can now go into our elastic potential energy equation. As we know from previous problems, the elastic potential energy is equal to half k x2 squared minus x1 squared. And since in position 1, It's unstretched, so x1 is 0. However, when we plug in our known values, we can get the elastic potential energy equal to 0.59 J. Okay, now the gravitational potential energy. And as we know, the gravitational potential energy is equal to mg z2 minus z1. And in position 1, z is 0 because the bar is still exactly horizontal. So, if you plug in what we know, we've got mg, and z2 is going to be equal to, if we go back here, it's going to be equal to minus b over 2, which is this length over here, b over 2 sine theta max. So, minus b over 2 sine theta max but we don't have the mass yet, so we're going to leave this equation on hold for now. Now for the kinetic energy, we know that T is equal to half I/O omega squared. However, delta T is going to be equal to T2 minus T1. We know that the position 1 T1 is 0 because it's at rest. However, also at T2, the T2 is 0 because because at T2 it's at max rotation. Therefore, omega, or the angular velocity, is also 0. Therefore, the change in kinetic energy is 0. Now that we've got all of that, we can then plug all of that into the work energy equation, which is U equal to delta T plus delta Vg plus delta Vs. And there's no external work, so U is 0. If we plug all of that in, we get 0 is equal to minus m multiplied by 9.81, 0.2 sine 30, plus the potential energy of the spring, which is 0.59, to get a final answer of the mass, which is 1.2 kilograms. Now for part B, they were asking for the magnitude of angular velocity when theta is 15 degrees. Okay, so we're just going to repeat the previous steps to find L2. So L2, we're just going to plug in that same equation we found over here, but plug in 15 degrees in the theta. So 0.2 over 4 under the square root 6 sine 15 minus 18 cosine 15 plus 19. That's going to give us an L2 of 0.089 meters. Now the change of length in the spring is going to be equal to 0.089 minus the unstretched length, which is 0.05, giving us a value of 0.039 meters. And then again, we're going to plug in our values into the elastic potential energy equation, which is half 200 0.039 squared to give us a value of 0.152 joules. we're going to plug in our same values into the gravitational potential equation, which is mass is 1.2 multiplies by 9.81 and minus 0.2 over 2 sine 15 for the Z2 to give us a final value of minus 0.305 joules. For the kinetic energy, delta T is going to be equal to half I-O omega squared. Now, for I-O, the rotational inertia, it's going to be equal to 1/3 mv squared. This is because this is the rotational inertia of a bar rotating about an axis through one end of the bar. So the bar is rotating at O, not around its center. Now that we found that equation, we just need to plug in our values to get the rotational inertia equal to 0.016 kilograms meters squared. And then when we plug that into our kinetic energy equation, we're left with omega squared that we're trying to find. And then we plug all of that into our work energy equation. To find the angular velocity equal to 4.37 radians per second going clockwise. And that's the final answer. Now for the second question, it says here that the center of a 200-pound wheel with centroidal radius of gyration of 4 inches has a velocity of 2 feet per second down the incline in the position shown. Calculate the normal reaction N under the wheels as it rolls past position A. Assume that no slipping occurs. Now for me, these units are completely different from what I'm used to. So it's important that we note down our known values and also our conversions. So we know that the mass, or actually the weight, not the mass, is 200 pounds. Now this 200 pounds is a unit of force, not a unit of mass. It's important to know that. Our radius of gyration K is 4 inches, or 0.33 feet. Now to convert from inches to feet, it's going to be divided by 12. So inches divided by 12 is equal to feet. Yeah, and then we've also got our velocity, which is 2 feet per second, and we want to find the normal force A. Now, as usual with these kind of problems, we need to start off with a free body diagram. So this is our incline, our wheel at position 1, and our wheel at position A, where it's not inclined. This is our weight. It's moving with a velocity v. Our angle 30 degrees. This is our normal force on the wheel. And the radius from this point here to this point here is going to be 2 feet. So 24 inches, 2 feet is 2 feet. The radius is 0.5 feet of the wheel. And the distance from here to the center of the wheel is 1 feet. Okay. The angle of the incline, this angle over here, is going to be equal to this angle over here, which is 30 degrees. Now I think we're ready to start a problem. So, first of all, our gravitational acceleration, g, in those units is equal to 32.2 feet per second squared. It's important to note that from the beginning. Now we're going to first write our work energy equation, which is U is equal to delta Vg plus delta T. There's no external forces included in this question, so U is 0. The gravitational potential energy is going to be equal to mg z2 minus z1. And when we plug in our known values, mg is equal to 200, and our z2 is going to be equal to 0 because it's going to be laying at the bottom of the incline, so it's going to be 0. And since z1 is the only one we're considering, so it's going to be negative. Now, first of all, we want to find the distance from the center to the incline, to the end of the linear incline. So if you imagine our center moving up to here, we want to find this distance over here. Now, since we've got the angles and we've got the length from C to this position over here, it's easy to find that, which is going to be equal to 1 sine 30. So here we've got 1 sine 30. So we're going to add that to this distance over here. So we need this distance over here. Now we can easily find the distance from here to here, right? But to get that distance here, we need to subtract that from this distance over here to get this distance over here. So how do we do that? Now the way I do that is by cutting this triangle over here at this point where the center of the ball meets the end of the inclined curve. And that way we can get this distance, which is supposed to be first of all, to find this total distance over here, it's just going to be equal to 2, so that's the total distance of the radius, 2 feet minus 0.5 feet, which is the radius of the wheel. So this is the total distance over here. So plus 2 minus 0.5. And we want to subtract this guy over here, which means once we have the angle theta 30 and our distance 2 minus 0.5 feet, which is 1.5, we can then easily equate it to 1.5 cosine 30. So again, let me just iterate that this portion over here is just equal to 1.5, the total distance, minus 1.5 cosine 30 for this distance over here. So okay, so once we found that and plugged in our known values, we get Vg is equal to minus 140.2 joules. Now for our kinetic energy, we know it's half IC omega 2 squared minus omega 1 squared. Now our IC is going to be equal to m k squared plus r squared. This portion is the radius of gyration, and this portion is for the radius of the wheel. And when we plug in our known values, remember that 200 pounds is a unit of force, so we need to divide that by our gravity, which is 32.2, multiplied by the radius of gyration plus the radius of the wheel to get an IC of 2.24 pounds feet per second squared. That's our rotational inertia. Okay, now that we found that, we want to find omega 1. And omega 1 is just going to be equal to, recalling back to our, if we recall back to our vector rotation equations, we know that V1 is equal to omega 1r, which means that omega 1 is equal to 2 over 0.5, which is 4 radians per second. We're going to do the same thing to find omega 2. So omega 2 is just going to be V2 over 0.5 or 2V2. And when we plug that into our kinetic energy equation, we get half 2.24 4V2 squared minus 4 squared. And now we can plug that into our work energy equation, which gives us 0 is equal to half 2.24 4V2 squared minus 4 squared minus 140.2, because that's the gravitational potential, to calculate V2 equal to 5.94 feet per second squared. Okay, wonderful. Now that we've got the velocity of 2, we can now finally do our sum of forces. So Newton's second law to find the normal reaction. So we're going to take the sum of forces in the n, so with our y positive, going up is equal to MAN, and with our angular motion relation equations, we know that AN is equal to omega squared r or v squared r. So when we plug in our known values for v and r, 5.94 squared over 1.5, we get the normal acceleration equal to 23.5 feet per second squared. Now for sum of forces, if we go back to our free body diagram, we have n minus omega, so n minus 200 is equal to the mass, which is 200 over 32.2, multiplied by the acceleration, which we just found, 23.5, and that will give us a final answer of 346 pounds. Now for our final problem, we've got a planetary gear system shown where the gear teeth are omitted from the figure. Each of the three identical planet gears, A, B, and C, have a mass of 0.8 kilograms and a radius of 50 millimeters, and a radius of gyration of 30 millimeters about its center. The spider E has a mass of 1.2 kilograms and a radius of gyration of 60 millimeters. The ring gear D has a radius of 150 millimeters and is fixed. So if a torque of 5 newtons meter is applied to the shaft of the spider at O, determine the magnitude of the initial angular acceleration of the spider. Okay, so there's a lot of variables here that we need to consider. So first of all, we're going to write down our variables. So we've got mg, which is the mass of the planetary gears, is equal to 0.8 kilograms. We have a radius of 50 millimeters, or 0.05 meters. We also have a radius of gyration of 13 millimeters, or 0.03 meters. The mass of E, the spider, is 1.2 kilogram, and it has a radius of gyration of 60 millimeters, or 0.06 meters. The radius of D, the whole wheel, is 150 millimeters, or 0.15 meters. And the moment applied, the torque applied, M, is equal to 5 Newton meters. And we want to find the angular acceleration of the spider E. So we're going to start off with a free body diagram. So from here, from O to the edge, that's R, and let's call the point in the middle P. So from the center of the gear, the radius is R, and the torque of M is applied. So theta is going this way. The gear, the center of the gear, is moving this way, and it's accelerating the alpha. So the tangential acceleration of the center is going to be this way. However, the gear itself is also rotating around its axis in the opposite direction, so it's actually moving this way. So even though the center of the gear is moving anti-clockwise, the gear itself is rotating around its own axis clockwise. Now that we've done with our free body diagram, now we're going to go on to our work energy equations. So we know that du is equal to dTe plus dTg, where g is the gears. So du, we have an external force applied with a torque M, so it's going to be m d theta, and our dTe is going to be simply d half IO omega squared. To simplify that, we're going to take the derivative of this expression over here. So it's going to be equal to IO omega d omega. And as we previously know from our angular relations, we know that v dv is equal to a ds. So if we translate that to our angular equations, we get omega d omega is equal to alpha d theta. It's exactly the same concept. And now for our gears, the kinetic energy of our gears, we have 3 gears in total. So each one is going to have d half ig omega g squared plus, so this portion over here is the wheel rotating on its own axis, right? And then another portion where it's half ma vp squared, and this portion over here is center of the wheel p moving anti-clockwise. So this is what the two portions are for. And now if we simplify that, we get 3 multiplied by ig alpha g d theta g plus ma vp dv. Sorry. So ma actually is just mass of the gears. So it's supposed to be mg. Now if we simplify that further, this expression over here can be simplified further to give us Vp dv is also equal to apt dsp. This is the same expression as this one. So vdv is equal to ads. And now we're free to find the value for dsp, d theta, apt, and basically all the other ones. So ig, alpha g. We need to find an expression for all of those. So let's start with dsp. What does that even mean? We want the distance that the planetary gears were traveling. So that's going to be equal to, if we go back to our free body diagram, that's going to be equal to this distance over here, which is r, big R minus small r, multiplied by d theta. That's just the distance around the curve in radians. On the other hand, if we want to find d theta g, it's going to be equal to that distance that we just found over the small radius of each planetary gear. So that's going to give us r over big R over small r minus small r d theta. Now for Vp, Vp is just going to be equal to big R minus small r theta dot, because V is equal to r theta dot. And the angular velocity, as we know, is Vp is equal to Vp over r. So that's just going to be big R minus small r theta dot over small r. Let me simplify that a bit more. Stay consistent. And now we also need to find the tangential acceleration, so APT. And as we know, it's just going to be equal to r minus r alpha. So AT is equal to r alpha. And alpha g, the angular acceleration of the gears, the planetary gears, is just going to be equal to the tangential acceleration over r. That's going to give us big R over small r minus small r multiplied by alpha E. Okay, now that we've got all of our values, oh yeah, no, we need to also find, we also need to find IG. I haven't found that yet. So IG is just going to be equal to mg multiplied by the radius of gyration squared, and IO is going to be equal to the mass of E, the spider, multiplied by the radius of gyration of the spider squared. Now that we've got all our values, we can now plug in our equations. dTg is just going to be equal to 3 multiplied by IA alpha theta plus mg r minus r squared d theta. And now we can derive this expression to get 3r minus r squared. We're still not going to derive anything. I'm still simplifying it further before I derive it to make it easier. I keep writing A, I don't know why. It's mg. Alpha d theta. And now actually, if we plug in our expression into our work energy equation, we get m d theta is equal to alpha theta multiplied by IO, that's our VG, our DTE, that's our kinetic energy of the spider. So IO multiplied by alpha d theta plus 3r minus r squared IG over r squared plus mg. So those two cancel out, we won't need to derive anything. And now we can finally just plug in our known values. So it's going to be 5 is equal to alpha E multiplied by 1.2, 0.06 squared plus 3, 0.15 minus 0.05 squared multiplied by 0.8 multiplied by 0.03 squared over our radius 0.05 squared plus the mass of the gears, which is 0.8. This is a big question. And now that we've got all of our values, we can easily find the angular acceleration of E, which is now equal to 135 radians per second squared. And that's the end of our problem. Thank you everyone for watching this video. I hope you enjoyed it and you understood the problems to solve, and good luck with your finals in a few weeks. If you have any questions, make sure you leave your comments in the comments below, or email me at noor.duidar@mail.utoronto.ca. As always, see you next week.